The Genesis echo. It was not darkness. Darkness is the absence of light, and there was no light to be absent. It was not silence, for silence requires space for sound waves to cease, and space itself was not yet a concept. There was only the singularity, an infinitely small, infinitely dense point of absolute potential, where the forces that would one day govern suns and atoms were unified, indistinct, and trapped. Time was not measured. It simply wasn't. For an eternity, a word utterly meaningless in this context, the 0 point existed, poised at the knife edge of creation. Then, in an instant that defined all instants that would follow, the universe spoke. It was not a boom, but a release, a catastrophic, glorious unbinding of energy that expanded faster than thought. In that first, unfathomably small fraction of a second, the universe experienced inflation, expanding exponentially. The unified force fractured, giving birth to the four fundamental forces that rule all things. The Genesis echo. Prologue. The 0 point. It was not darkness. Darkness is the absence of light, and there was no light to be absent. It was not silence, for silence requires space for sound waves to cease, and space itself was not yet a concept. There was only the singularity, an infinitely small, infinitely dense point of absolute potential, where the forces that would one day govern suns and atoms were unified, indistinct, and trapped. Time was not measured. It simply wasn't. For an eternity, a word utterly meaningless in this context, the 0 point existed, poised at the knife edge of creation. Then, in an instant that defined all instants that would follow, the universe spoke. It was not a boom, but a release, a catastrophic, glorious unbinding of energy that expanded faster than thought. In that first, unfathomably small fraction of a second, the universe experienced inflation, expanding exponentially. The unified force fractured, giving birth to the four fundamental forces that rule all things: gravity, electromagnetism, and the strong and weak nuclear forces. Time began. Space began. Matter was born from pure energy in a moment so searingly hot, trillions upon trillions of degrees, that all existence was an opaque soup of elementary particles. Quarks, leptons, and their antimatter counterparts annihilated each other in a fierce, chaotic dance, leaving behind a minuscule, inexplicable excess of matter. This was the cosmic fog, a swirling, thick plasma where light was trapped, unable to travel even the smallest distance before being scattered by free-roaming electrons. The universe was brilliant, yet perfectly opaque. The explosion of creation continued to expand, but it began to cool. For 380,000 years, the universe labored in this heat. Finally, the temperature dropped enough, to a mere 3,000 degrees Celsius, for the free electrons to be captured by the newly formed protons and helium nuclei. The atoms became electrically neutral. And in that moment, the cosmic fog lifted. Light, finally freed from the plasma, flooded the newly clear cosmos. It shot out in all directions, the first pure radiation, illuminating a universe that had hitherto been veiled in its own heat. This ancient light, stretched and cooled by the universe's relentless expansion over billions of years, is the cosmic microwave background, CMB, the fossil whisper of creation. The stage was set. The raw materials, vast clouds of hydrogen and helium, were scattered across an ever-growing, yet dark, void. The Dark Ages and the Architects of Matter. The universe entered the Dark Ages. There were no stars, no galaxies, only the vast emptiness permeated by a thin, cold gas and the faint, residual afterglow of the Big Bang. It was a period of overwhelming inaction, yet deep within the void, a silent, relentless sculptor began its work. Gravity. Gravity is the fundamental architect of all beauty and horror in the cosmos. It knows no rest, demanding only that mass be drawn to mass. In the newly formed universe, the gas was not perfectly uniform. Some patches were slightly denser than others. Tiny, statistical ripples left over from the chaos of inflation. These were the seeds. Over hundreds of millions of years, gravity patiently worked on these meager density fluctuations. It drew the thin hydrogen and helium gas inward, slowly at first, then with increasing urgency. The invisible scaffolding of dark matter, a mysterious substance that provided the gravitational backbone but emitted no light, guided the gas into immense three-dimensional nets. Imagine a fine cosmic thread slowly being pulled taut, gathering dew along its length. That dew was the primordial gas. As the gaseous clouds collapsed, they shrank, their material molecules accelerating and colliding with greater frequency. This motion generated immense heat. At the core of the largest, most dense knots of matter, the temperature and pressure finally reached a critical threshold, 10 million degrees Celsius. The protons, forced into intolerable proximity, overcame their electrical repulsion. Nuclear fusion ignited. The first stars were born. These were the population 3 stars, majestic, terrifying, and ephemerally short-lived. Unlike stars that would later follow, these giants were made only of hydrogen and helium, the basic building blocks of creation. Without the heavier elements, metals, to act as coolants, these stars had to be enormous, hundreds of times the mass of our future sun, just to stabilize. They burned with a furious blue-white light, tearing through the remaining darkness. They were solitary beacons, short-lived monuments in the immense void. Their purpose was elemental. They were the universe's first forges. Deep within their incandescent hearts, under pressures unimaginable, they began the process of cosmic alchemy. They fused hydrogen into helium, then helium into carbon, oxygen, nitrogen, and iron. Every element heavier than lithium, the foundation of all rock, water, and life, was being manufactured for the very first time. The stars, in their desperate brilliance, were signing their own death warrants. Burning their fuel at a furious pace, they exhausted their cores in mere millions of years, a fleeting blink in the age of the cosmos. And then they died. The galactic loom. The massive stars collapsed catastrophically. The iron core, the heaviest element they could fuse without inputting energy, could no longer withstand the weight of the star. It buckled, imploded, and then rebounded in a terrifying detonation. A supernova. It was the most spectacular, violent event in the universe. The energy released surpassed the lifetime output of 100 normal suns. The blast wave tore through the surrounding gas, but more importantly, it performed the final crucial acts of elemental creation. In the chaotic, high-energy environment of the explosion, the final heaviest elements, gold, silver, uranium, were synthesized. The first dust was scattered. As the supernova debris rained down upon the neighboring cold hydrogen clouds, it polluted the pristine material with all the necessary ingredients for complex chemistry. The universe was no longer just gas. It was now stardust. Over vast tracts of time, billions of years, gravity continued to pull. Not just gas, but gas mixed with the new dust. These immense, churning, swirling clouds of stars, gas, and dust gathered into the majestic, spiraling structures that would define the cosmos. Galaxies. Our story now moves to a specific, average galactic arm, 9.2 billion years after the Big Bang, where a dense, cold cloud of gas and debris, enriched by the sacrifice of countless population 3 stars, awaited its trigger. This cloud, rich in carbon, oxygen, silicon, and iron, was the cradle of the solar system.
The cradle of the sun. 9 billion years had passed since the Great Release. The universe, once a chaotic fog, was now structured into billions of swirling galaxies. Within the vast, spiraling disk of the Milky Way, in one of its outer, less populated arms, the Orion arm, lay a massive, cold molecular cloud. This cloud was a vast stellar nursery, hundreds of light years across. It was not pristine hydrogen and helium, but a rich, complex mixture, a cosmic stew containing all the elements forged in the hearts and explosions of countless long-dead stars. Silicon, iron, magnesium, oxygen, carbon. This was the ultimate inheritance of creation, the dust from which worlds are made. The cloud was stable, cold, and quiet, held in a delicate balance between the outward pressure of its thin gas and the inward pull of its own gravity. It waited. The trigger. The delicate balance was shattered by a violent interruption, the shock wave of a nearby supernova. Imagine a pebble dropped into a still pond. The wave, though brief, is enough to momentarily compress the water. A tremendous wave of energy, traveling at hundreds of kilometers per second, slammed into the edge of the molecular cloud. This shock wave acted as a cosmic fist, compressing a region of the cloud to a critical density. Gravity, now given a concentrated mass to work with, overwhelmed the outward pressure. The core of the compressed region began to collapse inward with terrifying speed, an event known as gravitational collapse. As the cloud fragment shrank, 2 vital things happened. 1, it heated up. The vast amount of gas falling inward generated enormous friction and pressure, converting gravitational energy into thermal energy. 2, it spun faster. Due to the conservation of angular momentum, the same principle that makes an ice skater speed up when they pull their arms in, the collapsing mass began to spin with increasing fury. The protosolar disk. The spinning material flattened into a vast rotating structure, the protoplanetary disk, or more specifically, the protosolar nebula. At its very center, 99.8% of the material gathered into an incandescent ball destined to become the sun. Surrounding it was a swirling pancake of gas and dust stretching billions of kilometers into the void. The vast difference in temperature across this disk dictated the fundamental architecture of the future solar system. The inner system, close to the sun, here temperatures soared, evaporating all the lightweight, volatile materials like water ice, methane, and hydrogen gas. Only the highly resistant, heavy elements, rock and metal, could condense and solidify. The outer system, far from the sun, beyond a certain boundary, the frost line, it was cold enough for water ice and other ices to survive and condense into solid flakes, providing vastly more material for objects to grow. The sun ignites. At the heart of the nebula, the protosun continued to accumulate mass. The pressure and temperature climbed to the ultimate threshold, 15 million degrees Celsius. The nuclear force was unleashed, and hydrogen atoms began to fuse into helium. The light and heat were spectacular. The protosun became a full-fledged star. A tremendous outflow of particles, the solar wind, erupted from the newly ignited sun. This immense blast swept through the remaining gas and dust in the inner solar system, clearing the nebula and leaving behind a much smaller, denser ring of rocky material. The long process of stellar birth was over. The stage was set for planet formation. The architects of worlds. The inner solar system was now a dizzying, turbulent zone of tiny rock and metal grains, left behind by the solar wind. The transition from scattered dust to solid planets was governed by a multi-stage process called accretion. The sticky dust. The first stage was simple electrostatics. Tiny grains of dust, like lint in a room, bumped into each other and stuck together, forming millimeter-sized clumps. Over thousands of years, these clumps collided and merged into pebble-sized, then boulder-sized objects. The planetesimals. As the objects grew, a crucial shift occurred. Gravity began to take over from electrostatic forces. When the rocky bodies reached a diameter of about 1 kilometer, they became planetesimals, small planets. These planetesimals were gravitationally dominant in their local area, able to attract and scoop up all the remaining dust and smaller rocks. The inner solar system, where Earth was forming, became a cosmic pinball machine. Millions of planetesimals orbited the young sun, their paths occasionally intersecting with devastating results. The proto-Earth was one of the largest planetesimals, relentlessly sweeping up debris. The constant bombardment of high-velocity objects generated tremendous heat, keeping the young planet in a molten, plastic state. It was a race between time and mass. The planet that grew the fastest and became the biggest was the one that survived. The Great Migration and Differentiation. As Earth grew, the planet's internal structure began to change due to the heat generated by impacts and the decay of radioactive elements. The heavy, dense materials, primarily iron and nickel, sunk toward the center, displacing the lighter silicate or rocky materials. This process, called planetary differentiation, separated the planet into its distinct layers. A core, a searing, hot, dense iron core. A mantle, a vast layer of molten and partially molten rock surrounding the core. A crust, the thinnest, lightest layer which would eventually solidify on the surface. 4.5 billion years ago, the bombardment was reaching its peak. Proto-Earth, a fiery sphere of molten rock and iron, was nearly complete, a world of unimaginable heat and violence, primed for the defining event of its youth. The Theia Impact. 4.5 billion years ago, Proto-Earth was a searing, magnificent sphere of molten rock, vastly larger than any of its remaining neighbors in the inner solar system. Its gravity dominated its orbital path, but the final massive collision, the event that would define its future, was yet to come. The Theia Impact was roughly the size of Mars, a formidable body with its own differentiated core and mantle, following a slightly unstable orbit that was tragically destined to intersect with Earth's. The Cataclysm. The collision was not a glancing blow, but an oblique, catastrophic impact. Theia struck the proto-Earth at a relatively slow angle by cosmic standards, a blow so immense that it can scarcely be imagined. The energy released instantly vaporized huge portions of Theia and ripped away vast chunks of Earth's outer mantle and crust. The entire globe shuddered, its newly differentiated layers momentarily remixed. The heat was so intense that the Earth became a roaring, superheated orb of lava and gas, enveloped in an atmosphere of vaporized rock. The impact effectively reset the geological clock of the planet. The birth of the Moon. The collision debris, a massive cloud of molten silicate rock and vaporized iron from both Theia and Earth's mantle, was ejected high into orbit. This incandescent ring of debris began to orbit the Earth, held captive by the combined gravity of the post-impact planet. Incredibly fast, perhaps within mere months or even weeks,
this orbiting material began to coalesce. Gravity, the great sculptor, worked swiftly on the orbiting rubble. The bits of magma and vapor stuck together, drawing in more and more mass. The ring rapidly clumped into a single large body, the Moon. The newly formed Moon was incredibly close to Earth, appearing massive in the sky of the young planet, and it was still glowing with the heat of its chaotic birth. The consequences of the blow. The Theia impact was the most destructive and yet most constructive event in Earth's youth. It yielded three profound, lasting consequences. Number one, the stabilizer. The Moon's immense size and proximity stabilized Earth's rotational axis, preventing the wild, erratic tilts that would have made long-term climate stability impossible. It became the great moderator, the keeper of seasons. Number two, the core. The force of the collision likely accelerated the final sinking of iron and nickel into Earth's core, helping to create the massive, rotating liquid iron outer core. This motion is what generates Earth's magnetic field, the invisible shield that protects the planet from the sun's deadly radiation. Number three, the atmosphere. Much of the Earth's original, lighter atmosphere was blasted away, replaced by volcanic outgassing from the post-impact planet, and setting the stage for the next crucial phase, cooling. With the Moon in place, the frenetic, violent phase of accretion was finally drawing to a close. The planet had survived its greatest trial and was now ready to begin the long, agonizing process.
The first ocean. As the crust cooled further, the water began to pool in the lowest-lying areas, the great valleys and basins that formed between the nascent tectonic plates. These were the first oceans. They were not the clear blue waters of today. They were likely hot, acidic, and dark, enriched by dissolved minerals and salts leached from the hot volcanic rock. This early ocean was a chemical soup, essential for the next step. Crucially, the process was a feedback loop. Cooling creates rain. Rain cools the surface faster. Cooling surface allows more liquid water to pool. The oceans began to consume the massive amounts of carbon dioxide in the atmosphere. The CO2 dissolved into the water, reacting with dissolved calcium and other minerals to form carbonates, which then precipitated out and settled on the ocean floor as rock. This process effectively sequestered billions of tons of greenhouse gas, thinning the atmosphere and preventing Earth from becoming a permanent Venus-like runaway greenhouse world. The Earth had found its blue hue. The hydrosphere was born. The iron heart and the magnetic shield. While the surface was being transformed by water, the engine deep inside the planet was reaching its final form. The process of planetary differentiation, the sinking of heavy materials, had concluded. The dynamic core. Earth's core settled into two distinct regions. One, inner core, a solid sphere of pure iron and nickel compressed by unbelievable pressure. And two, the outer core, a layer of superheated liquid iron and nickel that surrounded the inner core. The immense heat difference between the Earth's solid inner core and the slightly cooler liquid outer core created tremendous convection currents, slow, churning flows of molten metal. As the Earth rotated, these powerful currents in the conductive liquid metal began to generate an electric field. This is the geodynamo, the process that generates Earth's powerful magnetic field, which extends thousands of kilometers into space. The invisible protector. This magnetic field became Earth's indispensable guardian, the magnetosphere. The young sun, though less powerful than today, was erratic and was constantly bombarding the solar system with the deadly stream of charged particles known as the solar wind. When the solar wind encountered Earth's magnetic field, it was deflected harmlessly around the planet, channeled toward the poles. Without this shield, the sun's radiation would have continuously stripped away the young atmosphere and boiled away the surface oceans. The formation of the magnetic field was the ultimate precondition for long-term habitability.
The Earth now had a solid surface, liquid water, and a robust defense system. The setting of the stage. 4 billion years ago, the bombardment slowed to a trickle. The Hadean Eon was giving way to the Archean Eon, meaning beginning. The early atmosphere. The atmosphere was now much thinner than before, but still completely inhospitable to any modern life. It was a mixture of nitrogen, mostly inert but the dominant gas, carbon dioxide, reduced but still abundant, water vapor from ocean evaporation, and trace amounts of methane, ammonia, and sulfur compounds. Crucially, there was almost no free oxygen, O2. The sky was likely a hazy orange-brown color, and the sun shone dimly through the thick air. The first islands. Beneath the oceans, the tectonic activity that would one day move continents was starting. Massive eruptions of lava, particularly at mid-ocean ridges, began to build up basaltic rock. Over millions of years, these volcanic pileups broke the surface of the vast ocean, forming the first small, unstable proto-continents, tiny, isolated islands of land. The world was entirely dominated by water, rock, and gas. All the inanimate ingredients for life had been assembled: the complex atoms forged in stars, the energy from the sun, the protective magnetic field, the massive solvent of the ocean, and a protective, stable temperature range. The greatest chemical experiment in the universe was about to begin in the primordial soup of the sea. All that remained was the spark. The spark of life. The early Earth, roughly 4 billion years ago, was a world of violent beauty. Vast, warm oceans covered the planet, pierced only by smoky volcanic islands. The atmosphere was a protective blanket of nitrogen and carbon dioxide, completely devoid of the free oxygen that modern life depends on. It was a world of pure chemistry. The ocean, now our primordial soup, was rich in elements and compounds. The chemical ingredients were all present, but they remained inanimate. The challenge was to find an energy source to drive simple molecules to link up into complex chains. The energy sources required to turn simple chemicals into the building blocks of life came from several fierce, localized sources. 1. Lightning storms. The thick, energetic atmosphere was constantly swept by colossal lightning strikes, which provided electrical energy to rearrange atmospheric gases and dissolve them into the water. 2. UV radiation. Without an ozone layer, which requires oxygen, ultraviolet radiation from the sun was constantly bombarding the surface of the planet and the upper layers of the ocean, driving chemical reactions. 3. Hydrothermal vents. Perhaps the most potent source was deep underwater. Along the seams of the newly forming tectonic plates, scalding hot mineral-rich water erupted from the crust through hydrothermal vents. These vents provided a stable, dark, energy-rich, and chemically diverse environment, protected from the violent surface. Driven by these forces, simple molecules began to bond. Carbon, hydrogen, oxygen, and nitrogen atoms linked together to form the first organic molecules, the building blocks of life. Amino acids, the basis of proteins. Nucleotides, the basis of genetic material, RNA and DNA. These building blocks accumulated, concentrated in specific areas, perhaps in the tiny pores of rocks around hydrothermal vents or in shrinking pools along volcanic coastlines. Through processes of heating, cooling, evaporation, and catalysis, these molecules began to spontaneously assemble into larger, more complex chains, the first rudimentary proteins and RNA strands.
The first self-replicator. The true moment of creation, abiogenesis, occurred when a chemical system gained the ability to replicate itself. It wasn't life as we know it, but rather a self-sustaining chemical reaction contained within a simple membrane. The most likely candidate for this crucial step is RNA. This molecule is unique because it can both store genetic information, like DNA, and catalyze reactions, like proteins. In the RNA world hypothesis, the first self-replicating systems were based entirely on RNA. These RNA strands, enclosed in tiny fat-based bubbles, the precursors to cell membranes, began to consume the surrounding organic soup and copy themselves.
Imperfections in the copying process led to slight variations, introducing the concept of mutation and therefore evolution. The moment a flawed copy outcompeted a perfect copy, life had begun. The reign of the blue-green slime. 3.5 billion years ago, the oceans were no longer just a chemical soup. They were home to the leuca, the last universal common ancestor, the simple cell from which all life on Earth is descended. The archaea and bacteria. The first true life forms were simple, single-celled organisms, the prokaryotes, which include the archaea and bacteria. They lived off the chemicals in the ocean, chemosynthesis, or by absorbing the remaining organic molecules, heterotrophs. The world was microbial. A specific group of bacteria, however, would forever alter the planet's destiny, the cyanobacteria, the blue-green algae. The oxygen catastrophe. Cyanobacteria developed the ability to use the immense energy of the sun to synthesize their own food from water and carbon dioxide. This process is photosynthesis. It was an evolutionary superpower, freeing them from the scarcity of the chemical soup. The chemical equation of photosynthesis had a revolutionary byproduct, free oxygen, O2. For over 1 billion years, these tiny organisms relentlessly pumped oxygen into the oceans. Initially, the oxygen was absorbed by dissolved iron in the water, forming massive deposits of iron oxide on the seabed, the banded iron formations. Once the oceans became saturated, the oxygen began to bubble up and dissolve into the atmosphere. Slowly, inexorably, the composition of the atmosphere began to change. Around 2.4 billion years ago, the accumulation reached a critical mass, leading to the Great Oxidation Event, GOE. For the vast majority of life forms that had evolved in the absence of oxygen, anaerobic organisms, this new gas was a deadly poison. It triggered the first great mass extinction, known chillingly as the oxygen catastrophe. The planet's climate plummeted into a period of extreme glaciation known as Snowball Earth. Yet, for those few organisms that could tolerate, or better yet, use oxygen, this gas was a profound gift, enabling a far more energetic form of metabolism. The long geological saga of creation, from the Big Bang's energy to the formation of the planet's core, crust, and oceans, had culminated in the transformation of the very air. The Earth was now fully built, armed with its magnetic shield, covered in water, and powered by the energy of life. The stage was set for the eons of evolution to follow. The billion-year grind. The Proterozoic Eon. The Great Oxidation Event was not an ending, but a brutal billion-year bottleneck. The sudden flood of toxic oxygen created a hostile new environment, culling the vast majority of life that had evolved in the anaerobic world. Only those microbial communities capable of tolerating or utilizing this volatile new gas survived. The survivors were forced into an evolutionary arms race with the very air they breathed. This next chapter of Earth's story, the Proterozoic Eon, would be long, quiet, and deceptively slow. Yet its innovations would be the most profound since the genesis of the first cell. The rise of the oxygen consumers. In the shallow seas and deep sediments, life found two pathways to deal with the deadly O2. Avoidance. Many anaerobic organisms retreated into oxygen-free zones, deep muds, anoxic water layers, and the depths of hydrothermal systems. Utilization. A few pioneering bacteria developed complex enzymes that could handle and eventually harness the powerful reactivity of oxygen.
This gave rise to aerobic respiration, a metabolic process exponentially more efficient than any previous method. These new bacteria could generate far more energy from the same amount of food, giving them a monumental competitive advantage. The Great Merger, endosymbiosis. Around 2 billion years ago, a revolutionary event occurred, an act of cellular cooperation that changed life forever. Imagine a large, simple cell, perhaps an ancestral archaea, engulfing a smaller, highly efficient bacterium, one of the new oxygen users. Ordinarily, the larger cell would digest the smaller, but in this case, the larger cell kept the smaller one alive. The relationship was mutually beneficial. The large cell provided the smaller bacterium protection and a constant supply of nutrients. The smaller bacterium, now trapped inside, acted as a biological power plant, using its aerobic respiration to generate a massive surplus of energy in the form of ATP for the host cell. This internal power plant evolved into the mitochondrion, the engine of almost all complex life today. A similar event, involving a different bacterium, led to the formation of chloroplasts in plant-like cells, enabling enhanced photosynthesis. This merger, called endosymbiosis, was the moment the eukaryotic cell was born, the cell with a nucleus, mitochondria, and complex internal machinery. It was the crucial technological leap from a mud shack to a metropolis, unlocking the potential for true, visible life. The dawn of multicellularity. The first eukaryotes were still single-celled, but their complexity allowed them to grow larger and develop specialized structures. Once a cell had achieved this complexity, the path to joining forces with others became inevitable. The earliest forms of multicellular life were simple colonies, clumps of identical cells that stuck together perhaps for safety or to gain size advantages. But around 600 million years ago, a critical transition occurred: cellular specialization. A group of cells would begin to differentiate, some forming structures for locomotion, others for reproduction, and others for nutrient absorption. They were no longer just a colony. They were a single, integrated organism.
The Great Dying. The flourishing diversity of the Paleozoic era came to a sudden, terrible end. About 252 million years ago, between the Permian and Triassic periods, a cataclysm occurred that dwarfs all others: the Permian-Triassic extinction event, or the Great Dying. The Siberian Traps. The primary driver of the extinction was an unprecedented volcanic event in what is now Siberia. Over the course of perhaps 2 million years, colossal fissures in the Earth's crust erupted, pouring out an unimaginable volume of lava, a phenomenon known as the Siberian Traps. This supervolcanism released immense amounts of gases, sulfur dioxide, carbon dioxide, and methane, into the atmosphere, triggering a cascade of environmental destruction. 1. Global warming. The massive CO2 and methane release triggered a rapid, severe spike in global temperatures. 2. Ocean acidification and anoxia. The warming severely disrupted ocean currents and chemistry, causing the deep ocean to become starved of oxygen, anoxic, and highly acidic. The collapse of life. The result was the near sterilization of the planet. Marine life. Over 96% of all marine species perished. The ocean became a toxic, suffocating graveyard. Terrestrial life. Nearly 70% of land vertebrate species were wiped out. The vast coal forests collapsed. The Great Dying was a geological reset button. The complex, interwoven ecosystems of the Paleozoic era vanished, leaving behind a scarred, barren world dominated by fungal blooms feeding on the dead wood. But extinctions, while devastating, are also opportunities. The vacant niches created by the cataclysm would soon be filled by the survivors, a new class of reptiles that would come to dominate the Earth for the next 180 million years. The reign of the giants. The survivors of the Permian extinction rapidly diversified in the ensuing Mesozoic era, the Middle Life, an age defined by the dominance of the great reptiles, the dinosaurs. The Triassic and Jurassic periods. The first dinosaurs appeared in the Triassic period and grew to prominence in the lush Jurassic period. The continents had briefly reassembled into a final supercontinent Pangaea before beginning their slow, final breakup. The climate was generally warm and humid, creating perfect conditions for vast forests of conifers and cycads. Dinosaurs evolved incredible diversity, ranging from the tiny, agile hunters to the colossal, long-necked sauropods that shook the ground with every step. Their dominance was total. Meanwhile, the ancestors of mammals were small, nocturnal, shrew-like creatures, living literally in the shadows of the giants. A smaller, yet profound evolution was occurring in the skies. The refinement of scales into feathers, a feature found in many dinosaurs that led, eventually, to the birds. The Cretaceous climax. The Cretaceous period saw the dinosaurs reach their evolutionary peak, but also witnessed the appearance of another game-changer, the flowering plants, or angiosperms. Their coevolution with pollinating insects led to a brilliant burst of color and complexity, transforming the global flora. The age of the giants was at its climax. Then, 66 million years ago, the cosmic echo returned to Earth not as a whisper, but as a hammer blow. The final cataclysm. A massive asteroid, estimated to be 10 to 15 kilometers wide, struck the Earth near the Yucatan Peninsula. The impact released energy equivalent to billions of atomic bombs, instantly vaporizing rock and sending a blast wave that incinerated everything for thousands of kilometers. Most devastatingly, it threw vast amounts of pulverized rock, dust, and vaporized sulfur high into the atmosphere, blocking the sun globally for years. The resulting impact winter plunged the planet into darkness and cold for years. Photosynthesis shut down, the food chain collapsed, and 75% of all life on Earth died, including every non-avian dinosaur. The great age of the reptiles was over. The stage, once again, was cleared. The age of mammals and the echo. The world that emerged from the global winter of the impact event was sparse and cold, but full of opportunity. The small, resilient mammals, having survived by being warm-blooded, burrowing, and giving birth to live young, now inherited the Earth. The Cenozoic era, the new life, the last 66 million years, is the age of the mammals. With the pressure of the dinosaurs gone, mammals diversified wildly, filling every empty niche, returning to the sea, whales, soaring in the air, bats, and growing to immense sizes, megafauna. The continents continued to drift toward their current positions. As tectonic plates collided, mountain ranges, like the Himalayas and the Rockies, were thrust up. The evolutionary finale. In Africa, around 6 million years ago, a crucial line of primates began to evolve, hominids. Climate shifts causing forests to retreat and grasslands to expand pushed these primates out of the trees and onto two legs. Bipedalism freed the hands. The final decisive evolutionary leap was the development of the large, complex brain. Over millions of years, the simple impulse to survive morphed into curiosity, tool-making, language, and culture. The long cosmic journey, from the first particles of matter to the first complex organisms, culminated in a species capable of understanding its own origin. The Genesis echo. 13.8 billion years after the singularity exploded, and 4.54 billion years after gravity built the Earth, a creature stood on its surface. This creature, Homo sapiens, was made of the same hydrogen forged in the first moments of the Big Bang, the same carbon and iron cooked in the hearts of long-dead stars, the same calcium that armored the first life in the Cambrian seas. The Earth, a blue jewel forged in fire, polished by water, and armored by a magnetic shield, had fulfilled its potential. The Genesis echo, the initial cosmic whisper of creation, had finally achieved self-awareness. The universe, through the improbable crucible of Earth, had found a voice to tell its own story. The journey was not an accident, but the inevitable consequence of a universe governed by gravity, chemistry, and the relentless, irreversible drive of life.